page just for a second. Yesterday we were discussing the connection between continuity. Okay, is a graph continuous? Are you able to draw it without lifting up your pencil? And differentiability. Like I said yesterday, good luck saying that word. Does the derivative exist, aka the slope exist? So on page 179, kind of towards the top, we wrote down two things that must happen graphically in order for a derivative or a slope to exist. Did we have those two down written? It has to be continuous, and the slope from the left must equal the slope from the right. I just want to go ahead and just discuss or jot down what those two things mean, because even though you have them down in your notes, that doesn't mean you necessarily understand them. So let's go ahead and kind of rephrase them perhaps. If you know a graph is continuous, can you describe what the graph looks like? What the graph has or doesn't have going on it? Good, Braden?
It doesn't have a whole jump or an asymptote.
No whole, jump, or asymptote. I'm going to abbreviate. Now we know that's not the mathematical definition of continuity. That's how you can think about it. Okay, we know we have to use the three-part definition of continuity if we're going to state something or justify something, but that's how you can think about it in terms of a graph. Okay, yesterday we were looking at this idea of differentiability. Okay, if a derivative or a slope exists, so in order for the slope from the left to match the slope from the right, what might a graph look like, aka have or not have, in this instance? What are some of those key characteristics that we identified yesterday where a derivative doesn't exist? Maybe look at the three graphs. We identified specific locations or things going on those graphs. Yeah?
There's no end point.
No end point. Yep.
No vertical slope and no peak sharp point.
There you go. No vertical slope. All right. And the last one, you could say peak, sharp point, cusp. I've also seen corner sometimes. But anything that has like a drastic change to it, some type of sharp corner or edge, whatever word or phrase you want to use is fine. I tend to use sharp point. I know I've seen on the AP test before cusp. Okay, but I want you to be familiar that they mean the same thing. Okay, so what we're going to practice today before we continue with the notes, did everyone get a little half sheet of paper? Okay, everyone freaked out because they thought it was a quiz, but it's not. Okay, we're going to go ahead and practice identifying graphically where a derivative doesn't exist, aka it's not differentiable. So keep these ideas in mind. Okay, it has to be continuous, meaning no hole, no jump, no asymptote, and the slope from the left has to match the slope from the right, meaning no endpoint, no vertical slope, no sharp point. Okay, so can we reference this little page here for a second? So take a look at your first graph. If you were to look at the entire graph, can we identify some x locations where a derivative or slope would not exist? There are some issues. Go ahead, Braden.
X equals -4.
-4, so -2, -3, okay, so at this x value, why does the derivative not exist there?
There's a
Sharp point. So x equals -4 because sharp point. That's fine. Now hopefully you realize if this was like on a test or quiz, you would use complete sentences, right? Okay, but we'll abbreviate now. The derivative doesn't exist there because there's a sharp point. Are there other spots where a derivative doesn't exist on that same graph? Good, Vinny? Why -5? It's an endpoint. Good, Dan?
0.
Why 0?
Because it's a jump.
It's a jump. Okay, jump, you could also say discontinuous. Any one of those? Is there another one? You want to go ahead, Dan? We'll round that to 4. Yep.
Because that is an endpoint.
That's an endpoint too. All right. So if those are the places where the derivative does not exist, that means any other location you pick, the derivative does exist, meaning you can plot a point, you can draw only one tangent line, and you could possibly figure out what the slope of that tangent line is. Go, Dan?
Would one occur at like 2.5 because that kind of looks like it's semi-vertical at some point, and I remember we did one of those like a day or two ago.
Yeah, if you want to, I'd say so. Maybe. If you want to throw that one in there too, that's okay. 2.5-ish.
Yeah. And what was the word for that again? I got it.
Vertical slope.
Okay.
Or vertical tangent. Either one of those is fine. Looks good. We getting the hang of it? Kind of better than yesterday? I know we had examples yesterday, but not that had multiple things going on like this one did. Okay, let's move on to number 2. Can you find some x locations where a derivative doesn't exist? You cannot plot a point, or you cannot plot a point and draw one tangent line. Think about no hole, no jump, no asymptote, or hole, jump, asymptote, all those other characteristics. Go to Ariana.
X equals 3 because of the sharp point.
Yep. All right, there are multiple tangent lines that could be drawn there, so how on earth do you know what the slope of just one of them is? Right? So sharp point, derivative doesn't exist. What about any other locations? Good, Braden?
X equals 0 because
There's an asymptote. It's not drawn in, but notice how the two sides, they're never ever going to meet. Okay, so x equals 0 because you have an asymptote, aka discontinuous, whatever wording or phrasing you want to use. It looks like we don't have any endpoints, right? Because we have the arrows going on either direction. So that looks good. All right, let's try 3. Bottom one. Where does a derivative not exist? Go to Ariana.
X equals 4 because of the sharp point.
Sharp point. Looks good. You have another one? Go ahead.
X equals 5 because of the endpoint.
Okay. Good, Braden?
X equals -1 for vertical slope.
That one I'd definitely say. I could see where Dan was going with 2.5-ish on the other one because they do look kind of similar. This one, though, is kind of very exaggerated, and they will definitely be exaggerated on a quiz or a test, so you know for sure that that's vertical there. So x equals -1 because we have a vertical slope. I think that's about it. Looks good. All right, last one. Yeah.
-1 because of a jump.
-1 because of a jump. Okay. You could say jump or discontinuous. Yeah.
2 because of the sharp point.
Sharp point. You're on a roll. Yep.
3 because of an endpoint.
4.
4.
4. Okay. I know it's not labeled. Yeah, but we'll say it's 4. Yeah. -4. Okay. Looks good, right? So realistically, if you were to pick any other x value, maybe for instance -2, you could physically plot a point, and there is only one tangent line that you could draw at that spot that's not vertical. Because notice how you could draw a only one tangent line here, but it happens to be vertical, meaning the slope doesn't exist. So what we're looking for are places where that's not possible. You cannot plot a point, or you can plot a point, but there are multiple tangent lines, or it's a vertical slope, something like that. Did that activity help a little bit? Okay, so in order for a derivative to exist, you have to be continuous, meaning no hole, no jump, no asymptote, and you also have to have equaling slopes on either sides. Okay, meaning no endpoint, no sharp point, no vertical slope. So we're going to continue to investigate that today. Where did my paper go? All right. I believe we finished the 2 examples at the bottom of page 179. Is that right?
Yes.
All right, we're going to check out a few more of those today. So let's flip the page. For what values of k and m will the function be both continuous and differentiable? So we have to check 2 things, okay? There's no hole, no jump, no asymptote, but there's also no sharp point, no endpoint, no vertical slope, something like that. Maybe we'll start with continuity first. How do you want to check for continuity, specifically at 3? Yeah?
Point, and then the second one would be the limits, and then see if they match up.
Yep. Okay, we're going to use our 3-part definition for continuity. So we got to first check that the point exists at 3. So if you were to plug in 3, which equation would you use? The first one? Okay, so we're only going to plug in 3 for the x value. Remember, k and m are numbers that we're eventually going to try to figure out. So if we plug in 3, looks like we'll have k square roots of 4, which is 2k. So we know there's a point because k is eventually going to be a number, so that we know a point exists. Let's go ahead and check out the limits. We got to approach 3 from the left and the right. So according to the piecewise function, the left-hand side of 3 is the first equation, and the right-hand side of 3 is the second. I know it's been a while since we've done limits, but what do we always try first in a limit? Substitution. You haven't lost it. Good. All right, so go ahead and plug in 3. Looks like we'll get 2k again for the left-handed side, and 3m plus 2 for the right-handed side. So we check the point, we check the limit. The third piece, the point has to equal the limit. So is there some way we can combine maybe these results to write a statement showing that they have to be equal, or 2 things have to be the same? Let's see, in order for the limit to exist, the left side and the right side have to meet up, right? Have to match. So that means that this result and this result must be the same, right? They have to equal each other. But notice how the 2k and the 2k from the point are the same thing too. So by setting these 2 equal to each other, we're essentially setting the point equal to the limit as well, because these are showing up twice. So we can say the kicker, the 2k must equal the 3m plus 2. Do you guys see kind of an issue with that equation we have? Can we figure out what k and m are just off of that? No, you have one equation, 2 variables. Okay, it's not really balanced. So somehow we have to figure out what another equation is. Maybe we'll check out this differentiable aspect to see if something will pop up there. All right, so to determine if it's differentiable, we have to check to make sure that the slope from the left is the same as the slope from the right. Bless you, bless you. Okay, going for 3. Did I tell you guys I'm fascinated by people that can sneeze more than 2 times in a row? No? Maybe last year my kids knew. No? I've never sneezed more than 2 times in a row in my entire life. So when someone does 3 or 4 or 5, I'm like astounded by it. I've never done it. All right, so if you do it in here, you'll see me like get really excited because I've never ever done it. Don't force it though. Okay? Don't force it.
I love sneezing.
You love sneezing? You feel so good afterwards, right? All right, let's check out differentiable here. How can we check, or what do we need to find to figure out the slope from the left? When I say slope, you think tangent, aka derivative. Slope of tangent line, derivative, awesome. So if we were to write this out, we need the slope from the left-hand side, aka derivative, to equal the slope from the right-hand side, aka that derivative. So looking at your individual equations here, how might you want to find the derivative of both of them? Maybe we'll look at the first one. Remember, k is a number, okay, so we have k times the square root of x plus 1. I'm thinking chain 2. Yep, let's go ahead and rewrite it as x plus 1 to the 1/2 power. All right, so using our chain, notice how the outside pieces are k and then the power of a half. We would bring down the power of a half, so that would be 1/2 k. We keep the inside layer of that onion or gobstopper, whatever you think of. Don't forget your new power. Then we have to multiply by the derivative of the next layer. So what's the derivative of the x plus 1 inside part? Just 1. So if you're multiplying by 1, it doesn't really change anything. So this is representing the slope from the left. We need that to equal the slope from the right. Okay, so m is a number as well. What might the derivative of mx look like? Think about 4x, 5x, 10x, whatever. Yeah? Just m. Okay? And then you need to add the derivative of 2, but that's just 0, so why even bother? Okay? So we have slope from the left needing to equal the slope from the right, and we're specifically checking this x location of 3. So let's go ahead and plug in 3 to actually get the numbered value from the slope from the left and the slope from the right. Maybe you want to, some of us might want to rewrite this because you see that negative power there. You can move that to the bottom of a fraction, make the power positive. Maybe you want to turn it back to a root. The 2 is coming from the 1/2, 2 in the denominator, and we're left with a k up top. If you wanted to rewrite it. All right, so if we were to plug in 3 for x, what would we have left? K over 4 equals m. Okay? So let's not lose sight that the goal is to figure out what these constants are, k and m, in order for this piecewise function to be continuous but also differentiable. Okay, no hole, no jump, no asymptote, but also no endpoint, no sharp point, and no vertical slope. So how can we utilize these two equations to help us figure out k and m? Because now we have 2 equations with the same 2 variables. It's balanced, right? We should be able to figure it out. We kind of did something like this earlier this year. Yeah?
Would you be able to do that equation instead of the other one?
Yep. If m is k divided by 4, we can plug that in. Substitution. All right, so we should be able to solve for k. Let's see. This would be 3/4 k plus 2. We can subtract 3/4 to the other side. So 2 minus 3/4 would be 2 1/4. sorry, 1 1/4. That's if you add it. By the way, my pregnancy brain has been to the max lately, so that's going on these days. Okay, so 1 1/4. Can we write 1 1/4 as a fraction? Maybe it's been a while. 1 1/4. Can you turn a mixed number into a fraction? Right? Multiply, add. You get 5/4. Okay? So we have 5/4 k equals 2. Multiply the 4 over, divide the 5. K equals 5/8. All right. Let's go ahead and take that k value, plug it back into either equation you want to figure out what m is. I think the second one, even though it's a fraction, is a little bit easier to work with. There's less going on. So if you plug in 5/8 in for that k, there's not 5/8. Oh my god. I told you guys, pregnancy brain to the max. Ryan, you were probably mentioning that earlier, right? You kept saying 8/5. Oh my gosh. Okay. 8/5 divided by 4. We got 8/20. AKA 2/5. How about I just quit and I let you guys run the show? Is that better? Oh. Dear golly. We doing okay? Continuity should be review, right? Check those 3 things. Differentiability is new, but it's a similar concept, right? You're just doing derivatives. Okay, checking for slopes. Let's try a similar one. Find the values of a and b so that the function is differentiable. Okay, now something we kind of mentioned yesterday. Whenever you see the word differentiable, what does that also mean or tell you or imply? If the slope exists, what do you also know? Differentiability implies, yeah, it's continuous. Okay, continuous too. So even though it doesn't specifically say find the values for a and b where the function will be continuous and differentiable, like the last one was worded, just the fact that it says differentiable also means continuity. Because if the derivative exists, there is no hole, there's no jump, and there's no asymptote, meaning you are continuous. So this one is very similar to the one we just did, even though the directions aren't necessarily worded exactly the same. So let's go ahead and check continuity. We need it to be continuous in order for it to be differentiable. And it looks like we're checking out the x location of 1. If you were to plug in 1, which equation would you use? The first one. We're going to plug it in for all the x's. So we'd have 3a plus 2b plus 1. Let's go ahead and check out the limit. We got to approach 1 from the left, but also 1 from the right. According to the piecewise function, the first equation is on the left-hand side, and the second is on the right. Okay. First step in a limit, always try substitution. Alright, so we checked the point, we checked the limit. We need the point and the limit to match. Notice how the point already matches one side of the limit, right? So the point has to match the other side in order for it to be continuous. And that's a pretty long equation. Maybe we can clean it up a little bit. I don't care how you want to reorder things. It's completely up to you. Maybe I'll subtract the a over and get 2a. Add the 4 over, get 6b. Why not? We'll just add the 3 over and get 4. Set it equal to 0. But you can reorder however you feel comfortable. Now, if our goal is to figure out a and b numbers here, we only have one equation with two variables. It's not balanced. So somehow we have to figure out another equation to help us use, or use to figure out a and b. So let's check out the differentiability part. Alright, so differentiability. The slope from the left has to equal the slope from the right. Slope, aka derivative. So if you were to take the derivative of the left-handed equation, what would it look like? Keep in mind a and b are numbers. A little tricky. Let's see, if you think about the first term, if you brought down that power of 2, you would have 6a, right? Isn't a number? Okay, so we'd have 6a, and then the new power on the x is just 1. So if you want to write it, go ahead, but you don't have to. If you took the derivative of the next term, brought down the power of 1, you would have 2b. New power would be 0, meaning your x is gone. And then we'd have to add the derivative of 1, which is just 0. So there's the derivative of the left-hand side. Let's try the derivative of the right-hand side. If we brought down 4, we'd have 4a. New power is 3. The next term, if we brought down the 2, we'd have 8b. New power is 1. I'm running out of room. And for the last term, if we brought down the power of 1, we'd have minus 3, and the x goes away. So we're showing that the slope from the left needs to equal the slope from the right. Let's go ahead and plug in 1, because we're specifically looking at that spot on the graph. Figure out the slope value at that spot. So 6a plus 2b needs to equal 4a minus 8b minus 3. Maybe you want to clean that one up a bit as well. We can subtract the 4 over, get 2a, add the 8 over, get 10b, have a negative 3 on the other side, completely up to you. But somehow we have to utilize these two equations to figure out a and b. What do you want to try? Do we like substitution? Do we want to do... There was another method called elimination. Maybe you guys remember that? Do we have a preference? You want to do elimination? Okay, so we got to line up all the a's, all the b's, all the equal signs, then all the numbers. So let's see, if we write 2a plus 10b equals negative 3, okay, this equation, we would need then the 2a plus 6b, but next we need an equal sign, which means we'd have to subtract that 4 over. That way it lines up with the number on the other side. Alright, so how do you guys want to go through elimination now that everything's lined up?
Change the size of the first line.
It doesn't matter, first or second.
By -1.
Yep. Multiply one of the equations by -1. Notice how the a coefficients already match. So we'll just change the signs on those values, multiply everything by -1, and we'll just add down. Okay, so the a's are going to eliminate, cancel out. Negative 10 plus 6. Looks like we got negative 4. 3 minus 4, negative 1. So solving for b, looks like we get 1/4. Alright, so pick either equation you want, either the blue one or my blue one from continuity or the red one for differentiability. Plug b back in and check out what a is. Super tiny down there, but I hope you guys can see it. I got negative 11/4. We doing okay with those fractions? Yeah?
So for the equation for the
Yep.
you set it to 0, and then for the other one you set it to -3.
Yep.
You want to do that for the other one too?
Like if you plugged this in for this one?
Oh, no, would you be able to put that equation
Yeah.
or
Yeah, you could make this 2a plus 10b plus 3 equals 0. That's fine.
Okay.
And then you could do elimination that way because everything's lined up. Yeah, that would work out. Okay? Negative 11/4. We're on the same page? Checking out? Alright, good deal. Alright, so two things from this section, kind of big ideas. We have to be able to identify graphically where a derivative doesn't exist. I think we did good on that activity, right? Okay. The other thing is, a little bit trickier because it's no longer pictures, it's actually math work, are using calculus concepts to determine where you're continuous but also possibly differentiable. So you have to use the three-part definition from continuity like we've already discussed, but now we're throwing in slope values, aka derivatives. Just checking sure or making sure that the slope from the left is the same as the slope from the right. Okay? Are we okay with those two concepts so far? I like the head nods. Okay. We'll end there for today. We'll pick up the next section tomorrow. Are there any questions on the homework you guys want to go over? Either from this section or previous ones, since we have a little bit of time left. You guys can hit me with your best shot. You do, yeah. Circle, star, do something, yep.
Number 3.
From this section, 181. Okay. Show analytically, okay, by hand, analytically means like by hand using algebra work, that h of x is in fact not differentiable at the x value that you identified in exercise 1. Show and explain your work. So when we did 1, I think we did that yesterday together, right? We said -6, 2, and 6 were the points, okay? Not differentiable at the x value you identified. Let's just go ahead and assume, even though we did 3 of them, okay, let's go ahead and assume that they're referring to the 2, the sharp point one. That's kind of a big one. So if we're going to show that it's not differentiable, that means the slope from the left is not the same as the slope from the right. They're not matching up. So we have to go ahead and figure out derivative equation for left-hand side and derivative equation for right-hand side. Did you try number 2?
Yeah.
Yeah, what was your equation?
Negative 1/2 x plus 2.
Okay.
And negative
Uh-huh.
20x minus 4 squared plus 5.
All right, that's wonderful. Can you give us a refresher on how you found those two? Because some people might be a little confused by that. How'd you get those two equations?
The first one's just a line.
Okay.
Use the slope and the y-intercept.
Okay, so from the line, he identified the slope and the y-intercept, which is pretty good from there. What about the second one?
And then the second one's a parabola, so I use the vertex. Is that what it's-
Vertex, yep.
And I just kind of guessed as to where to put the two numbers.
All right, so it moved right 4, which if you think about transformations is signifying a subtraction on the inside of a function. So we would need a -4. Then the vertex also moved up 5, which is signifying an addition on the outside of a function. It's also flipped upside down, meaning a reflection. So we have a negative on the outside as well. So you can write the equation of a line. You can also write the equation of a parabola using the vertex to help you out. Okay? So we need to show that the slope from the left is different from the slope from the right. Let's go ahead and check this location of 2 because that's where this function ends and this one begins. Okay, so for the left of 2, what would the derivative be from the first equation? If you were to find the derivative, -1/2. And if you were to find the derivative of the right equation, we got a chain. If you bring down the power of 2, you'll have a -2 out front. Keep the inside layer. New power would be 1. But then you got to finish with the derivative of the next layer. So what's the derivative of the inside? 1, so why even bother? Okay? So we know that the slope from the left is -1/2. The slope from the right is this quantity. We need to somehow show that if we plug in x equals 2, that they are not equal. Okay, the slopes are different, somehow creating a sharp point, a vertical slope, and end point, specifically sharp point in this case. So if you were to plug in 2 for x, we have -2 times -2, which is a +4. Clearly, the slope from the left is not matching the slope from the right. Is that okay, Braden? Yeah. Okay. Any other ones you guys want to check out? Number 4? All right, we're on a roll. Given the graph of h of x pictured above, find the equation of a tangent line to the graph of P, specifically at x equals 3. What do you need to know to write the equation of a tangent line? Point and slope. All right. Let's check out the point first. Okay, if you plugged in 3 into P, you would have the square root of h of 3. Can we figure out h of 3? The graph's at the top. All right, so then the square root of 4 is 2. There's your point value. All right. Slope meaning derivative, right? How do you want to figure out the derivative of P? If you look at the P equation, it's a chain. Let's rewrite it as h of x to the 1/2 power. Okay, so we would bring down the 1/2. We keep the h of x inside layer. New power would be -1/2. But you got to finish the chain by multiplying by the derivative of the next layer on the inside. So that would look like h prime because we're using function notation. If you want to simplify it, reorder things, that's fine. We do have a negative exponent, so something's going to move to the bottom of a fraction. Looks like we have a 2 already in the denominator. we'll have a square root of h of x down below, but then h prime is left up top. All right, so let's go ahead and plug in 3 to get our slope value. If you were to plug in 3 into the derivative, what would you get? Let's see, if you think about the graph, okay, if you think about the graph, this is the x location we're looking at, this is the point we would draw, and we could approximate a tangent line, right? Okay, you could approximately figure out what the slope is, but we already know what the equation is of this section, right? And didn't we already figure out the derivative of that section as well in part 3? Didn't we say this was the slope, aka derivative of the right-hand side? So if you were to plug in 3 into that x, what would you get as your derivative? 2. Okay, so when you plug in 3 into the derivative of h, you actually get 2. So that tangent line I drew roughly has a slope of 2, and if you check it out, kind of looks like it does, up 2 over 1. If we plug in 3 into the other x value, we would have h of 3, which we already said was 4. So solving from there, looks like we get 2 over 4, or a half. So with that point and that slope, you should be able to write your equation. I'll let you guys go from there. Alright. Bell's going to ring in a little bit. Okay, we're going to start the next section tomorrow. Just a reminder, partner quiz on Tuesday next week. Okay? Tuesday.